Our ideas have always been fueled by our technology, and fuel has always accelerated how we take our ideas and make them real. Coal accelerated our ideas for how the handmade could be machine-made. This propelled us and their ideas into the industrial age. The age of steam and steel. From here we made real our ideas for telegraph and railway networks, gas and water supply, electrical power and telephones. We've taken our first steps into today's connected age. And the fuel for this journey? Oil. Oil sparked an unprecedented boom. The industry grew so fast that regulators scrambled to control its rapid growth. Does any of this sound familiar? A fight over a valuable new commodity, fast unregulated growth? If it does, it's because we've discovered a new fuel for our ideas: data. Data is the new commodity being fought over, and the cloud is its pipeline. Data is the fuel that drives the 5 biggest companies in the world, all of them cloud companies. For Google, Amazon, Facebook, Apple, and Microsoft, the cloud is the new baseline. It's the cloud that's transforming the way all of us live our lives, the way we communicate, the way we travel, the way we relax. Software is eating the world, and the world of design is undergoing this same transformation. The cloud is already transforming the way you design and make things. Your designs no longer have to be confined inside little static boxes that live on or under your desk. No longer do you have to rely on the equally static representations of the things you make. And no longer do your products have to remain static as you send them out in the world for your customers to use. Your products, permanently connected, can live and grow out in the world. Just like your products, the cloud tools we all use are permanently connected, permanently growing. And this is leading to a profound transformation. Our tools and what you expect for them are undergoing metamorphosis. Let me show you what I mean. Let's start by looking at how our design tools are being transformed by the cloud. When computation was finite, we made tools that you directed. You had to direct the tool. You drew the lines and arcs that described your idea. You decided when to run simulation on a design to discover its performance. But now computation is abundant, we can flip the whole thing around. No longer simulating based on a design, and not just simulating during design, but simulating to discover the design. With generative design, you just need to describe the problem, the goals and constraints, the forces at play, and the tool helps you discover what's possible. It uses abundant compute power to analyze the entire solution space, discovering designs you would never have come up with. But generative design is also moving beyond just synthesizing geometry. It's starting to understand something infinitely more complex: the needs of people. Our team in Toronto has moved into a new building, and so we're using it as a living experiment. An experiment to discover how we could maximize productivity and create a great environment for the people working there. So we use generative design, but rather than feeding it the forces affecting an individual part, we fed it the forces influencing human productivity. We surveyed our employees and captured their preferences and work habits. The system then evaluated that survey data against a set of hard constraints: the boundaries of the building, the fixed locations of the stairwells, and so forth. And then it generated thousands of floor plans. The system sought to minimize distractions, maximize outside views, prioritize personal relationships, and find an equitable solution to everyone's needs. We weren't just pushing cubicles around like Lego blocks, and we weren't just stuck with the first idea that worked. Our traditional design tools passively awaited our instruction. The relationship was purely directive. We directed the tool. But this relationship has evolved into one that's adaptive. Our generative design tools anticipate our needs, and in doing so, help us discover the best design possible. And how about creating the things we design? Let's look at how the way we make things is being transformed by abundant compute power. The The physical capability of our robots hasn't changed drastically in decades, and nor has their environment. We still lock up our robots in the same old work cells. We do this to protect ourselves. These things move fast, weigh a ton, and have no way of seeing if we're in the way. But we also lock down our processes to protect our investment. We all followed the Six Sigma thinking of the 80s, streamlining our manufacturing, making it as lean and efficient as possible. With our processes rigidly locked down, we balance the economic equation with volume. But we can flip this equation on its head. Let me show you how. Meet our robot, Ash. Ash is no different than other robots, apart from the fact that we don't keep her locked in a cell. We're exploring how we can give Ash the freedom to 3D print in metal all on her own. Ash doesn't rely on us for direction. Instead, Ash works as part of a closed-loop system to self-correct as she prints. And as we build more capability into the capabilities of Ash, we need to build more flexibility into the way we work with her. By bringing Ash into a full-scale, real-time VR environment, we can step into her world and enjoy a closer relationship with her. We can interact with her intuitively and use our arms to manipulate hers, which means that the space she occupies is no longer such a barrier. The way we work with robots no longer has to be so rigid, thanks to VR. And by giving our robots new capabilities, the way robots work with us becomes more fluid. Let's look next at how abundant computing is transforming additive manufacturing. You probably know about our work with Airbus. You may have seen this cabin partition evolved using generative design. What you may not have seen is how a slime mold called Physarum drove the design of this panel. Physarum grows to connect food sources by building a very dense network of interconnections, weeding out less important connections and reinforcing more important ones. To design the partition, we created an algorithm that models the logic of Physarum. And in doing so, we created an object where form truly follows function. But when we printed the partition, we discovered how difficult it was to understand it. We couldn't see where the part might fail, even though the computer could. We could hold the component in our hands, but not in our heads. Similarly, our traditional tools might be able to simulate this component, but the whole, our structures, once so inspectable, are fast becoming inscrutable. Abundant computing is transforming the tools we use to design and make things. In turn, the very things we make are also becoming transformed by these tools. This partition embodies the evolutionary algorithms of generative design. This chair reflects just how far beyond our own limitations these tools can take us. And these floor plans reveal what's possible when we let go of our tool and let it direct us. Data is increasingly driving our design decisions, and as we capture increasing amounts of data, our traditional tools can't scale, and neither can we. Our tools and the things we make with them are turning into black boxes. But just because these black boxes are less inspectable, it doesn't make them any less capable. Far from it, in fact. The capability of modern machine learning techniques and the massive parallelism of the computing systems they run on are capable of solving ever bigger problems. They're capable and reliable. More reliable than their over-engineered predecessors. Often more reliable than we are, in fact. At facial recognition, at cancer detection, and at driving. Self-driving cars aren't built on if-then statements. They're built on insights. They don't run on formulas and functions. They're predictive, projective, and productive. Machine learning focuses on the principle of driving, not the formula. If-then statements are like the rear-view mirror. Autonomous systems look forwards and out into the world and learn from what they see there. We built our computational model at first on the conditional, but from this is emerging one engineered to be insightful. So what might our future Autodesk tools look like, transformed by machine learning? It Maybe some time before we get to self-driving everything. But what do the first steps look like? Let's revisit robotics and see how we can teach our robots to anticipate variability rather than require conformity. We can build Six Sigma solutions that aren't the sum of Six Sigma parts. By giving our robots computer vision, we give them the ability to see. So no longer are they blind to our presence. And by applying machine learning, we give them the ability to learn. So no longer are they blind to our processes. Rather than requiring the conformity of an assembly line, our robots can now learn to accommodate the variability of our disorderly human world. We introduced this robot, Bishop, to the very disorderly world of Lego. We built a machine with curiosity and let intelligence evolve. And so Bishop came to understand that he has eyes to see and a hand to grasp. He evolved a basic ability to react and respond to his environment. Then we accelerated his development by creating an artificial world for him to learn in. We replace what he sees by changing out the optical image for a rendered one made from physical simulations of Lego bricks that correspond to the real world. And with the goal of learning how to assemble the pieces, we fed a neural network this view of what Bishop would see. By decoupling the learning environment from Bishop's physical environment, we also decoupled time. The computer could now learn in computer time, grabbing and assembling millions of blocks overnight. And once this robot has learned the skill, the cloud means that all robots have learned it. And we can replace those Lego bricks with anything, so the robot can learn to grasp and assemble any object. So rather than relying on conformity, we can instead embrace variability. So, if a machine can learn how to build with Lego through observation, why can't a machine learn behavior of the tools we all use in the same way? What if we took a similar approach and used machine learning to cut through the complexity of something as challenging to master as Maya's fluid simulation tools? If Maya itself could learn these settings, all these settings, perhaps by manipulating each slider, dial, and drop down, and correlate these to the resulting rendered image, then it could do what visual effects artists do all the time. It could look at the reference photography, and from this use its intuition to infer the settings needed to recreate the effect digitally. Let's move from visual effects to how we're investigating how to make Moldflow a more insightful simulation tool. The 10,000 materials in the Moldflow materials database represent 30 years of data, all acquired by slow physical testing. And yet, 2/3 of the materials in the Moldflow database still don't have complete properties. Through physical testing, we'll never finish. But machine learning can help us scale. We can take the materials we do know and use them to predict those we don't yet know. We can't characterize across 10,000 items, but a neural network can. We're using such a network to extrapolate the data and complete the library for all 10,000 materials. And because this happens in computer time rather than human time, we won't have to wait years for that data to be complete. The best simulation code is effectively a model that calculates real-world performance. But by teaching an AI, by subjecting it to many inputs, we enable it to work not by calculation, but by intuition. Let's move from simulation to finish on how machine learning is transforming our tools for construction. Project IQ fits into the BIM 360 family. Real-world data for construction is at the center of IQ. 27 million documented issues from 10 years of BIM field data. IQ takes this data and uses machine learning to predict high-risk issues, project subcontractor risk, and keep superintendents productive. The supers at Swinnerton Construction use IQ to check potential risks on projects, just like they check on the weather forecast. We started by automating classification of the construction issues from the descriptions typed on site. It's like autocomplete for the construction site. Now we're moving IQ onto image analysis and deriving descriptions and classifications, directly from photos taken on site. The system applies reasoning that a picture of a sill that's damp underneath is likely a water leak from a poorly fitted window. It reasons that scaffold with missing guardrails is a potential safety risk. And what about subcontractor risk? If your subcontractor had a poor record on large-scale projects, wouldn't you want to know? It's like Waze flagging a pothole while you drive. You don't need to personally experience the pothole to know it's there. IQ's risk prediction model identifies patterns across vast amounts of historical data. So instead of looking at project management through a rearview mirror, IQ uses this data to help look forwards and out into the world, where it augments its knowledge about construction from what it learns there, in GPS data, weather data, and eventually maybe even actuarial data. So rather than follow a recipe, the data at the center of IQ allows it to reason through observation. Just as we need to let go of the wheel to fully realize the promise of self-driving cars, we also need to let go of our traditional tools. Only then will we realize their full potential. Imagine a world where computation remains finite. Your design stays confined in a box. And we confine our tools to boxes too. In this world, our tools would exhibit the rigid and somewhat logical characteristics we see here on the left. Now, imagine instead a parallel world where computation is abundant. We don't push finished products out into the world, and nor do you. Our tools remain permanently connected, permanently growing. And doing this, our tools, fueled by data, begin to transform into something much bigger, and so do your products. It's data that's the fuel for how machine learning is transforming the capabilities of all our products. And it's this transformation that's leading to the adoption of the more fluid and creative characteristics on the right. What's emerging from this transformation is something greater than the sum of all these parts. Tools capable of representing and comprehending what we design, our ideas, and the means of giving these ideas agency and embodiment. We let go of the tool and let the tool come to us. And in doing so, we find not only are our tools as logical and analytical as ever, but now they're also creative and intuitive. At Autodesk, we're designing these tools and imbuing them with the qualities of a true design partner, a partner which is not just good at execution, but which excels at exploration too. Together we can bring out the best in each other. Together we can make anything.